10 talks. I won't say too much tonight because my voice is dead. After this, we'll go to the Redo. So we have Subway catering. There's a long story there. Subway at the Redo with a tab as well for tonight. Afterwards, tonight we have Adriel talking. I think everyone here knows Adriel, but if you don't, he'll also introduce himself in a couple of minutes. There was another note I was going to make. That's pretty much it. This is the last event for this year's committee. So, apart from the AGM technically, I suppose. But yeah, I mean, there's not much actually to that, I suppose, except to say maybe come to AGM this Thursday. So if you want to elect for a committee position, the link is up on Discord, where you can also show up on the night and nominate yourself. Just come along, helps us make quorum so we don't disband, and then who knows what happens to the pizza money and everything else. But yeah, come along. If you want to be a part of the committee next year, or T3 or anything, chuck your name up. It's a lot of fun, very rewarding. I highly recommend it. So that's this Thursday at 5 p.m. Not in this room, but across the hall in S202. S201. One of those. It's across the hall over there. You'll see the big sign and everything. Yeah, this Thursday, I'll pass over to Adriel now.
Thank you very much. Nice transition. Hi everyone, I'm Adriel. I'm a third year mechatronics and engineering student. And I'm Pecco#2304 on Discord. I go by many names. Today we'll be talking about, of course, as promised, macro wizardry. We'll be working completely at the preprocessor level. So we'll be covering minimal C and C++, but the amount that you will need to know will be covered during the talk. So don't worry if you've never touched this before. Also, the stuff that I'll be presenting here is cursed. There are people that online have been doing this for far longer than I have, so I'll attribute URLs at the bottom of the slides if you want further information. Also, please don't use these techniques in production code. I think that should go without saying. Some of these things really break control flow and are quite hard to understand requiring an hour talk to go through it. So if any of you have any questions, please ask as we go through rather than at the end, because of the volume of content that we'll be covering. Great. So, firstly, what is a preprocessor? This diagram shows it's like a block diagram of a typical compiler chain. So if you execute GCC with C source code, this is kind of what happens to your source code as it goes through GCC and then pops out as an executable. And we're only really interested in the preprocessor section here. Specifically, it takes source code, you'll see, does some stuff, and then outputs preprocessed code that goes into the compiler, which is the next stage. What does it do? It removes comments. The compiler doesn't need to see your comments, so the preprocessor just searches for your comments and removes them. Also, for lines in your source code beginning with a hash character, it interprets them as special preprocessor directives, and we'll be covering what each of these do during the talk. You can essentially think of a preprocessor as cleaning up your source code and then delivering it to the compiler for the serious optimization, linking, whatever. So for macros, there are two types of macros in C language. First type is an object-like macro with syntax defined like this. So hash define the name of the macro and then whatever body it gets expanded to. So if we have an example, hash define pi is 3.14, then if we were to write float x equals pi over 2 and send this through the preprocessor, that would expand into float x equals 3.14 over 2, as we expect. So the preprocessor literally just looks for pi as a token there, and then it substitutes that with 3.14 in the text. Similarly, if we were to use it as a function call, so printf pi, then this would also expand into printf 3.14. If we put pi in quotes, the preprocessor is smart enough to understand that pi in quotes is a string and should not be expanded, so this gets left as is. Also, if I were to write pi rentf instead of printf, then it is also smart enough to know that pi rentf is not the same as just pi by itself, so it leaves that as is. And then similarly, for literals such as like 0x pi, not even valid, stuff like that, those get left as is, except for pi.3, where the dot actually ends the token there, and it does get expanded into 3.14. The second type of macro is a function-like macro, defined like this. So hash define function-like, and in parentheses, some parameter, and then it expands to the body there. An example would be a double macro like this. So hash define double x 2 times x. If we were to write double of 3, then this would expand into 2 times 3, where 3 would be substituted in for x as the argument. Similarly for y, even if y isn't defined in our program, the preprocessor doesn't care. It just sees the text, character y, and then it substitutes it in for y in the body definition. What if we had double 1 plus 2? Well, if this was a function, you'd expect that the entire 1 plus 2 will be passed to double, and then that would get multiplied by 2. But the preprocessor expands it as 2 times 1 plus 2, literally like that. And you can see that if we were to write this in C, the operator precedence will be incorrect. We would need brackets around the 1 plus 2 to get the desired behavior. And this shows that function-like macros aren't functions. They work at a text level. So just to be safe, we need to surround the argument in brackets and also just for good practice around the whole body in brackets. That's just a technicality. But just goes to show that this stuff is really working at the text level, not at the semantic level. Similarly, if we were to just write double by itself, the difference between a function-like macro and an object-like macro, of course without the parameter, is that double by itself doesn't expand to anything because we've supplied no arguments. And of course, if we were to pass that itself as an argument, we'd get 2 times 2 times x as expected. Double called with empty arguments, well, it does count as an argument, but it just places nothing after the asterisk. Cool. So we can define macros, function-like macros that take multiple arguments, as we'll see in the next slide, but there are some traps behind that. So what can we do so far? Just with the stuff that we've talked about in the past 2 slides, we can define stuff like this. So we have a double macro, as we just saw, with brackets, and negate, so just like multiplicative inverse, or additive inverse, sorry, and then adding 2 things together. We can also define these macros. Apply 1, f, and x, and its body expands to f brackets x. Similarly for apply 2, where f takes in 2 arguments. If we write apply 1 double 3, what would we expect that to have? Well, we'd expect that double is f, and then 3 is x. So that should expand to double of 3. Similarly for add 5, 6, and that's the next step. Then the preprocessor recognizes this as double of 3 and add 5, 6, which then expands to 2 times 3 and 5 times 6, as we expect. Also, if we define macros like this, first and second, which each take in 2 arguments and return the first and the second argument, we can do stuff like this. So first 1, 2 should be 1, second 5, 6 should be 6, as we expect. But then it would be a bit tricky, and instead of passing in values, we pass in function-like macros. Well, what does this happen? Nothing has changed here. The complexity is the same. First of double and negate, the first thing is still double. Second of double and negate, second thing is still negate. So we still have double 1 and negate 2, which then expand to 2 times 1 and minus 2 as we expected. But the important thing that I want to hammer here is that first and second expands just to the tokens that we give them, right? It's only because we've defined double and negate at the top that the preprocessor then interprets double 1 and negate 2 as these things here. If we didn't have that, then you would just be left as double 1 and negate 2. Cool. Essentially, we have higher order functions in a very loose sense of the word. And what's the first thing that we do when we have higher order functions? We compose them, right? So let's try to think about a macro that we can do to compose some function-like macros f and g. So we want to compose fg of x to expand to f of g of x. And as with before, that composed fg by itself needs to expand to some token where the preprocessor then interprets foo of x as a macro call. Does anyone have any ideas on how to do this? Because note it is quite difficult to accomplish this without lambda functions in your language. For example, in C with function pointers, it is very difficult. No one? Okay, here's a hint. Let's exploit what the composition looks like in text. We have f of g, f open bracket, g open bracket, and then x, and then 2 close brackets. So we can think of this as factoring this whole thing into the left section only dependent on f and g, and in the second section only dependent on x. If you just focus on the latter half here, let's define a macro id close 2, taking in one parameter where it expands to x and then 2 closed brackets, right? We can have unbalanced brackets in these macros. It doesn't care, it just only cares about substituting text. So here, define id equals 2 like this. And then what we'll do is with our compose macro, first we'll put f, open bracket, g, open bracket, and then id equals 2. So then, if we move to the next slide, if we try to expand out compose fg of x line by line, what do we have? By definition, f open bracket, g open bracket, id equals 2 applied to x. Then the latter half gets expanded into x close close, which is exactly what we want. Demo time. Okay, let's see how good my typing skills are. So one thing I just might get out right off the bat. GCC allows you to stop the compilation at the pre-processing stage by passing this -a argument, and we'll demonstrate that. So here I just have this compose.h file with our negate, double, and add, and our first and second. And here, these are just the, I might do it like that. This is just the definition that we had from the previous slide. So let's try compose fgx. And that might be a bit small. Let's see if I can increase the size of that a bit. Hopefully this is better for everyone. Okay, cool. So if I do gcc compose.h dash capital E, it prints out f of g of x as we expect. Now let's try with a concrete example. Instead of f and g, let's try compose double negate 1 with should do double of negate of 1 as we expect. We get error. Unterminated argument list invoking macro double. What has happened here? Well, what went wrong? This is our error message. Here is our expansion. Compose negate double 1. Whoa. The problem here is that the first two tokens are negate followed by an open bracket starts the argument list of negate because negate was defined before. Whoa, okay, sure. Because the preprocessor thinks that negate is a function like macro. So when it sees negate and then an open bracket, it immediately starts looking for an argument list. And because there's no close bracket there, it panics, right? This didn't happen with f before though, because f wasn't defined. We just said compose fg with some text f that the preprocessor didn't recognize. So here, we need to somehow delay the expansion of negate and double until everything else, id close 2, is fully expanded, right? So that way, the preprocessor won't get fooled by that. So, for delayed expansion, introducing nothing. Define a macro that is just blank. It expands to nothing, right? But what this does is, if we place a blank after f and g, so now we have f blank, open bracket, g blank, open bracket, then f blank, open bracket, gets expanded to f, open bracket, but after that, since we've already expanded id close 2 by that point, our whole string would be a valid argument list, right? So let's try that. If we do hash define blank, f blank, g blank. Let's just test that this still works. Yep, still gives us f of g of x. And this does give us double of negate of 1. But this is still not what we expect. We expect double and negate to be actually expanded. In other words, we want 2 times minus 1. Why is it not doing that? Well, we need to run it again, clearly. Actually, if I go back here and I take the output of this and run it back through the preprocessor, we see that we get 2 times minus 1 as we expect. So essentially, we need to run it again. Here's an excerpt from the very long and lengthy GCC compiler manual. Macro arguments are completely expanded before they're substituted in, and then afterward they're expanded again, TLDR, right? The result is that the arguments are scanned twice to expand macro calls in them. After delaying, after we've put in the blanks there, there's nothing else telling the preprocessor to expand them again. Because we've just said blank there, but there's nothing else that's triggering another expansion. So let's do it ourselves. Essentially, we need to put the output back into a body of another macro. And we can do this just via like an identity macro like this. So just define eval0 of x to x. And then if we wrap our whole thing before in eval0, that will then expand again, giving us what we want. But imagine you have a preprocessor program that has so much deferred evaluation, right? Sorry, deferred expansion. And you want to make sure that everything gets expanded and you don't want to keep typing eval0. Well, what do? Just do it more times, right? You can keep you can keep doing it. And with 5 levels of expansion, you get 3 to the 5 expansions, right? So if we wrap our compose in that new eval, then essentially with our new like this, we should get our result. Right, okay, so we have this eval chunk here, and eval compose negate. This thing, I'll delete this so we don't have that in the output. Bam, 2 times -1, as we expect. Awesome. Nice. Okay, so now that we have delayed expansion, we have high order functions, we have composition. Now, what if we want to try recursion? Because why not? Well, let's define a macro like this. Define a of x as 1 plus a of x take 1. Now, in any reasonable language, this wouldn't terminate, because if integers are unsigned, etc. And also, preprocessor is dumb enough that it doesn't even know what x take 1 is. So it will just keep expanding to x take 1, and you wouldn't know. But let's give it a try. Recurse.h, that's the one that we want. Okay, so this is spoilers. I did not clean this before. Nice. Okay. Hash define a of x as 1 plus a, x take 1. Let's try a of 10. And I might just evaluate that bash script that I showed before, just to save time. What does it show? 1 plus a, 10 take 1. So no recursion here, just literal substitution of 10 into our x's. I mean, what else did we expect, really? So, what if we still really want recursion? Well, here, I'm going to introduce some more compiler manual terminology. A self-reference is where a macro's name appears in its definition. And an indirect self-reference is where 2 macros expand to each other. Right? And the manual says, the self-reference is not considered a macro call. It's passed into the output unchanged, which is why before, when we had that self-reference of A in the body, it didn't get expanded again. Also, you might expect that double scan from before to expand the self-reference twice, but it doesn't. It actively prevents programmers from achieving recursion again. So eval, even if we try eval, it won't work with self-referential macros. And I'll just demonstrate that here. So eval A of 10. No. Oh, I didn't comment this out. Yeah, still the same thing, didn't work. Okay. What can we do? One weird trick, eval does work for indirect self-references, and I'll get to why this happens a bit later. Here's the trick. Make 2 macros with duplicate bodies, and then when they want to recurse, just call the other macro, right? Also, we need to defer the evaluation of both. Otherwise, after repeated evaluation, they'll just collapse afterwards. Okay, so here's how we'd apply this to our example. We define A1 and A2, where instead of A of x 1 plus A, we do 1 plus A2. And then A2 calls 1 plus A1. And then we also put blanks there to defer the evaluation. And then you may ask, it seems like the C Standards Committee really doesn't want recursive macros. And then I raise you, this issue, which was opened in 2001, had a most recent post in June this year. Not really active, but it's about whether this is undefined behavior. The consensus is no. Demo time. Okay. So, define blank again. Define A1 and A2. A2, A1, blank. And A1 of 10. Let's just try this. So it should call A2, as we expect. And then let's say we wrap it in eval. Congrats, you've achieved recursion. Very nice. So from now, all of the stuff I'll be showing is, well, okay, let's phrase it this way. the stuff that we've just seen before is not really that powerful. You can think that, oh well, we can change text and stuff, but from now on you'll see really what we can actually do. And that starts with this hash operator. And that actually concatenates the two tokens on the left and the right. So x double hash y expands to x prime. Okay? For some reason, this only works within the macro body, so you have to wrap it, you have to do like cat xy and stuff like that. And then even more, if an argument is concatenated, the pre-scan doesn't occur. So if you just put that in there, it doesn't actually expand it out, so you have to add another layer. Let's just do a demonstration. So, cat the page. Okay, let's try this. So here we have our double macro. We have our cat underscore, which is just the primitive concatenation here. And then we have another layer here, cat without underscore, which just forwards its arguments to cat underscore. So let's try cat of hello and double of 3. Double of 3 would be 2 times 3, as we expect. So that's not what we want. It gives us hello double 3, which is literally the concatenation of the stuff that we passed in. And this is what I meant before, that when we pass stuff to cat, it doesn't expand, right? For some reason, I don't know why. Okay, and then let's even try flipping the arguments. So if we do cat underscore double 3 hello, save that. Error, pasting close bracket and hello doesn't give a valid token because you can't end the token there at the close bracket. It doesn't make a token. Okay, sure. So what about let's expand it before we do that? If we do cat instead of cat underscore, we get hello 2 times 3 as we expect. And then if we do cat double 3 hello, we get 2 times 3 hello as we expect. So of course, for all reasonable intents and purposes, we'd just use the cat instead of cat underscore. Right? What can we do with concatenation? We can do lookup tables. Believe me or not, provided that the indices concatenate to form valid tokens. So here's an example. Boolean AND. Truth table, 2 arguments, yeah, like that, right? So we just have AND followed by 2 either zeros and ones. And then in our AND function, so AND macro, we just report the results of concatenating the token AND with the 2 arguments that we put in. For example, if x was 0 and y was 1, then this would expand to AND 0, 1, and then the preprocessor would see that as hash define AND 0, 1, which results to 0. Essentially, we've encoded the whole logic of AND by smashing stuff together and defining the results at AND. That's for those arguments. Okay, and then another one is just if. So this if takes in a Boolean, a function to report when it's true, and a function to report when it's false. We basically concatenate if with that Boolean, and then just call the result of that on true and on false. And these are just the first and second macros, just dressed up a little bit. But they do the same thing. On true, on false takes the second argument, on true takes the first argument. Nothing really special there. What can we do with this? Well, why not just define all of the other stuff here? Whoa, what's going on? Yeah, so essentially we can handle this for ands, for ors, for Boolean nots, all of the stuff there. And yeah, okay. We'll be coming back to that lookup table approach in a bit. I'm just going to talk about why commas are deceiving. So let's say if you had a macro like this, define foo as 1, 2, which seems dangerous because that's an unshielded comma. And you might be thinking, oh, where are we going to put that? That's dangerous, right? Next, add with xy is just our add macro. And then if you try to call add with foo, well, maybe you'd expect that that expands, so to get add 1, 2, maybe you'd think that, oh, that's only 1 argument, so it doesn't work. Well, no, it doesn't work. It requires 2 arguments, but only 1 given. So this shows that when a macro actually requests 2 arguments, but we only pass in 1 thing with 1, 2, it doesn't actually expand to fill the argument, which is sad. Also, this identity thing, if we say ID, and then print out before, x after, this just prints out before after, which indicates that, okay, well sure, then this is technically still 1 argument present. It's not no arguments present, as you'd expect in a language like Python, where it takes no arguments, and if you put in anything, it breaks. Cool. Yeah. Introducing var args. So var args is a method that allows a macro to take an arbitrary number of arguments, right? So in this case, if we define a head and a tail macro, For example, head expands to head, tail expands to varrox, which indicates, just stands for everything off the head, then we can do stuff. I'll show you in the demonstration. Yeah, I'll also show this in the demonstration. So let's just try this. Define head, dot, 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 head, define tail is expanding to whatever these triple dots are. And then let's see what the result of head 1, 2, 3 and tail 1, 2, 3 are. So head 1, 2, 3 is 1, as we expect, and tail 1, 2, 3 is 2, 3. The comma is included there. Okay, that's important. So what if we try doing the same thing that we did before? Define a macro foo with unshielded comments like that. And let's try calling head of foo and tail of foo. I'll comment these out. Yep, okay. What's going on here? Head of foo expands to 4, 5, 6, 7, and tail of foo expands to nothing. And that shows that we still have the same problem as before, right? Because even if you paste foo into that first argument, it doesn't expand to fill the variable arguments. That's not what we want here. What can we do though? By adding another layer of indirection. There's a quicker, so all programming problems can be solved with another layer of indirection. So here, we add fill f, where fill itself takes in the variable arguments, and then it just parrots out those variable arguments to f there. And if we try it now, it should give us what we want. This is just weird special behavior of varrox, and I don't know why they did it that way, but we can make use of it. So here, 4, 5, 6, 7, even though this is one, what happened to the pants? Okay, even though this is one argument to head, this still gets expanded in this fill section to call head on 4 and then tail on 5, 6, 7. Cool. Okay. Now, here's the spicy bit. We can use, just because commas were deceiving before, we can harness them to our advantage. Here we have control flow with commas. Let's say we want to write code to detect whether a number is 0, right? We've reached this far in the talk, and this is when we're doing this, right? Okay, so let's just define false as 0 and true as 1, just for readability. And we have our fill macro as earlier. Now, let's have is 0 with the 0 next to it. This is our truth table approach, right? With some placeholder and true. The main thing that I want to point out here is 0, 0 expands to two things, right? Two comma-separated things, right? And then if we have a second function which just takes the second in an argument list, then we can define is 0 by, first, concatenating our number to is 0, and then applying all of that to second. Let's go through an example of is 0 applied to 0. Okay. So, by definition, we substitute 0 into our x's, and then cat is 0 of 0, then expands to is 0, 0, which is the concatenation. But then here, we have fill, but this is 0, 0 expands to two tokens, because we've defined it as expanding to two things earlier. And then as we apply second, then the second thing here is true, because we've placed a placeholder before that to push it into the second position. Right? And note that if x isn't 0 here, let's say x was 1, then is 0, 1 would be left as one token. The preprocessor wouldn't recognize this as expanding to two things. So instead of having true here, instead of having a placeholder, we'll just have blank is 0, 1, and then false, in which case the second thing in the argument list would be false. Yeah.
Why use placeholder in second instead of just using first and not using placeholder and defining is 0, 0 to be true?
Sorry, say that again.
What if you define is 0, 0 to just be true without the placeholder, and then you just use second instead of first? I mean, use first instead of second.
Okay, I'll do it. Oh, wrong one. This one? That's not what I expected. Okay, let's just copy what was on the slide before. So, and what else? Hash define 0, 0, placeholder true. Hash define true 1, hash define false 0, hash define second, x second, var second. And then hash define is 0 with x as fill second, then cat of is 0 applied to x, false, and then we need to do cat from earlier. Cool. And then is 0, 0. Okay, so this gives 1 as we expect. So did you say before, instead of having this defined as placeholder true, just have that as true?
Yes. And then instead of using the second macro, you could use a first macro.
Okay, I'll show you where the problem with that is. So hash define first, x bar out x. Right. And then here would fill with first.
Yeah.
Okay, let's try that. So is 0 of 0 should give us 1. What about is 0 of 1, 2, 3? Is 0, 1, 2, 3? Right. What happened there? The reason why this fails is because cat is 0, x is still one positional argument. By defining is 0, number 0 as two things, we exploit that because the preprocessor recognizes that it's a 0. It expands into a different number of arguments as if it wasn't defined. Because if it wasn't defined, it would just have one token, no commas. If it is defined, it has 2 commas, or 1 comma, so 2 tokens.
Got it.
Right? So that's why we need the second macro to pick the second one. In case if it isn't defined, we already have a value there. If it is defined, we shove another thing in the argument list so that the second thing is now true. Right. I hope, does anyone else have any questions? Because this is quite tricky. No? Okay, cool. Right. So essentially, just the main idea is that we can conditionally define the output of a macro given some argument, as of so is 0, number 0. And then we've done it in such a way that when it's defined, it expands into a different number of comma-separated arguments, in this case 2, instead of if it wasn't defined, which is just 1. So then we select it, and then it expands and gets to true. So let's try defining a general repeat macro to repeat some macro n number of times. Okay, so I'll just do a demonstration because this is easiest. Okay, so most of the stuff is stuff that we've already seen before in the talk. Right, we have the false and the true. We have our evals for our recursion. We have our concatenation. We have fill. I'll just remove that because that's not used. We have our is 0. And here's something new. We just have a function that gives us the previous number. So just like 9 evaluates to 8, 8 evaluates to 7, and so on. Okay? And we have our boolean not here. We have our if here. And the only difference that we've done with the if is we've just made it work for numbers that aren't 0 or 1. We've just said that if of 3, 3 is a truthy value, it's non-zero. So let's just do on true instead. That's the only difference that this does. Okay. And then, as an extension to that, let's define our blank and our whole. Whole of x just takes in one argument and evaluates nothing, so it's like a blank but with one argument. And then define a when macro to say if the condition holds, let it just evaluate it, else expand to nothing. Okay. Here's our repeat macro, and you can see that here we're already doing that recursion trick that we mentioned before with the alternating defines here. So what we're going to do is when the number is non-zero, repeat, and in the recursion, we do 1 minus that number, right? And then of course we pass in the function and then the arguments. And then when we want to actually call the function, we just call it on 1 minus the number and whatever arguments that we pass in. Okay? And this DD thing, it's a double deferral. I'm not exactly sure why this is necessary, but just think of it as one deferral. And these two things call each other, of course, repeat references repeat 1, so we do need an eval on the outer part. If we just define number to be 6, and then this function m, which just prints out the first number, then calling this should give 0, 1, 2, 3, 4, 5, because it's recursed to such an extent that on every next iteration it decreases the argument value, etc., etc. And then it does so, it actually works from the right down. So it works from the right, starting from 6 minus 1, and then going down to 0. And that's how the recursion terminates, essentially. And then this is basically what we showed. Okay, another example. Just quick show of hands. Who here has done some functional programming? Any kind of Cool. So you'll recognize the stuff that we'll be showing on the next two slides are immediate, like very similar copies of how you define map and fold on lists in any functional programming language. So how do we represent a list? We can choose this representation. So we can say bracket 1, 2, 3, and then a closed bracket or pair of brackets to indicate the end of the list. Right. Firstly, to actually do any recursion on lists, we need like a kind of pattern matching thing, right? A head and then a tail. So we need to know when the end of the list is. Let's make a helper function to check for that open bracket, closed bracket. So firstly, this is going to be very similar to that detecting zero thing before, where we have this dummy thing which expands to 2 arguments. And essentially by expand out all of this, the main thing is that here, if ln is a pair of brackets, we're exploiting the fact that a pair of brackets preceded by a token can be interpreted as a macro. We're essentially exploiting that here. So if ln was brackets, then this would be dummy open and close brackets, which would then expand to 0, 1 end. Hence the adding and pushing additional arguments sort of thing. But the rest is just technicality. I'll send the slides after this if you want to have a more detailed look on what this is doing. It's very similar to the second thing before. So if we just take that as given, then we can define map and fold. For example, map takes in an f, and then an x, and then the next value. And what it does first is it applies f to x. And then we check whether the next value is the end of the list. And if it is, we apply whole, which destroys everything. But if it isn't, we apply map 1 to the resulting arguments, which is basically like a pattern matching thing. If the next item is the end of the list, we stop evaluation. Otherwise, we keep going and apply our map function to the remainder of the list. So we basically go along one element at a time. Similarly, for fold, we can use the fact that this checkend takes in any functions that we want. So instead of terminating on none, we can just accumulate the values in this first argument f here. And then when we're finished, we get the second argument and spit it out. Right? Because this is the second argument in this list. And then when we're finished, second will be called here, which will evaluate to this nested f and ab to get a fold. Okay, the meton. Let's see. Yeah, so this is basically what we had before. And also I've defined some Liberty concatenation things just to check it out. So if we have a list with A, B, C, and D in an empty pair of brackets, we can try map of double on that list. Map fold H, we get 2 times A, 2 times B as we expect. Right, works beautifully. Also, if we have fold, so we define a binary function add, taking in 2 arguments, then we can fold, add over the list to get A plus B plus C plus D as you'd expect. So those work. It took a long time to get those to work. Okay. Now we're going to transition into a different section of the talk where we talk about stuff that is more common to be used in C. For example, include, if, and endif. You'll probably see this as something like include test.h. Basically, if you didn't know what that does, it pastes the whole content of test.h into the current file. The preprocessor just grabs all of it, copies and pastes it into where it is in the current file. Right? And if and endif allow regions of code to be hidden depending on the condition that you pass. For example, hash define A to be 3. If A is larger than or equal to 1 plus true, then have this whole block evaluate the true, else false. Right? But this is a bit surprising because the preprocessor understands arithmetic and comparison, but only in the context of an if, which is very sad. Right? What if we had this before? Then we wouldn't need half an hour to talk about how to compare with a number of 0. Right? So that works, but only in the context of an if. And in this case, we can also shorten if and def x to be if not defined x, where defined just gives a Boolean value whether some token is defined. Right. So now that we've seen this behavior, that the preprocessor isn't dumb enough, and that it can understand arithmetic expressions, but only in the context of an if clause there. Okay, we'll well, here's a common usage actually. Shouldn't get ahead of myself. This is just an include card. If you've done C, you'll know what it is. If you haven't done C, this is basically what it does. So you put all of your stuff inside where it says declarations here, and then you check whether some token, some unique identifier is defined. If it is, then everything else gets hit. If it isn't, then you first define it, and then write your stuff. And this basically ensures that you don't define something multiple times. Okay, but really in all decent compilers, you should be using count once, but that's a side issue. Okay, can we exploit it? Of course we can. Okay, starting off with this language that I will refer to as BF, which has a link here, and I'll explain that now. Okay, cool. So this is an interpreter for BF programs that is written solely in C preprocessor macros. And I'll just show how this is done. So here, they have some makefile that auto-generates these header files. And each of these are just long tapes of next stuff and defining and all stuff like that. You can think of stuff like this as just an include a file level replacement of our eval macro before. Because remember, in the slides, if we were to use stuff like this, right? If we were to use stuff like this, we can't put an hash if inside a macro. We can't expand macros that contain hash if, right? So that means that our programming now needs to be done at a file level, not just at a macro level. So that's the reason why they have that kind of repeated evaluation now at the file level here. And wow, that is a lot of files. Oh my gosh. Okay, also, they've done stuff like this, so this is basically like repetitively including things until it halts. I mean, if it works, it works, all right? So, okay, let me just demonstrate this. I will just be running simple.bf here, and I calculated before JavaScript calculator, this should evaluate to the number 7. So, I'll do this, and if we go to main.h, you can see that what this has done is it's converted this whole text here into its binary representation, basically. So each character maps to each of these here, okay? And we should just be able to do make run. Okay, so this will take 5 minutes to evaluate. You can see that at the end of this README, it says, it is very, very inefficient and will use about 16 gigabytes of memory and needs 15 to 20 minutes of processing time when running a Hello World program. So I'll leave it there. Okay, next, what are we doing? Turing machine. I'm sure you guys all saw the description of the talk. Turing machine. So, how does this work? Okay. This is how I've encoded the instructions for a Turing machine, right? So the way to interpret this is that A, B, C, and D are the names of states, followed by an underscore, followed by the value in that specific cell in the table. So here, and then following that, we just go to like the specific state left or right, and then the ending state. And you can see that even though I'm not going to show the implementation here, this is kind of related to what we showed before about the pattern matching and the lookup tables, right? Because you could just do like A concatenate with whatever thing is in the table. And then the preprocessor would look for that and look for whatever it gets expanded to, and so on and so on. So even though I'm not showing the implementation, I hope maybe with the concatenation you can kind of see how this will be done. And to run this, they gave this, so I'll just make, this does a busy beaver program. Expand top. Okay, and I also wanted to do this, which should just visualize a little bit better. Okay, so these blank parentheses with a comma inside just indicates the continuation of the tape. So that would be just as it continues on forever and forever. And then you can see that from the top here, it looks for everything in this specific state, and then it goes to like one right, etc., and stuff like that. And then eventually we get to a halting state. That's how it's done. Now, you may ask from this, is the preprocessor Turing complete? aside from the infinite memory limitation that everyone seems to forget about these days, or not forget about, ignore these days, the answer is unfortunately not. Where is my mouse? Okay, cool. So if we go to the implementation limits, you can see here that the number of macros simultaneously defined is at least 4,095. The nesting includes only 200, levels of parenthesized expressions only 63. So these are the minimum requirements as guaranteed by the C standard. However, if the preprocessor doesn't actually have infinite, if it doesn't use up all memory, then I guess you could consider this as a separate limitation to the infinite memory thing, in that instead of having infinite memory, it cannot compute, it cannot expand infinitely. Right. Is our BF thing finished? Yes, it is. It's expanded to 7. Okay, very nice. Okay, okay. Nice to know. Lastly, Lisp interpreter, right? So this was another thing that I put as a description of the talk. This is which one was this? This file. Okay, so left defined, very, very scary things, like clearly with the unbalanced parentheses, they're doing all sorts of stuff. Left done an equality comparison by concatenating EQ with a token ln itself to indicate equality, and that there's the conditional expansion and everything. Very complicated, I don't get it, but it's cool, right? So, which one is that? Oh, just made a change. Okay. I believe, is it here? Nope, it is not there. Okay. Where is it? It is not there either. Where is the program? Oh, it's in tests. Okay, cool. So here, this is just one of the test files that can evaluate. So they're representing the Lisp, kind of like the S expressions as this nested sort of every token is within a pair of brackets kind of thing. That's an alternate representation of lists to what we had before. But if we do tests basic primitives.h, you can see that this does in fact expand to Lisp code that I've defined here. And they also have managed to get Lambda, which I haven't got my head around, but it's very impressive. So go check out these links if you're interested in more. And one thing that I might conclude with some resources, these are some libraries that people have written containing all of the macros that we've defined earlier, just to make life easier when developing in the preprocessor world. So the first one is made by the same person who initially wrote the repeat macro. The second one is the boost preprocessor library, and I want to show one part of that. So here, we've actually encoded data types. Actually, I'll make this black so people's eyes aren't blinded. Okay, so we have data types now. We're encoding arrays by having its length, and then comma-separated arguments. Left on lists like this, which is a more faithful functional kind of thing, where you have one list and then the entire tail as another list. They have sequences that look like this, and they have tuples, which just look like that. So clearly it's a very robust, popular, I don't know if it's popular, is any of this popular? I don't know. Library that has been developed to do this stuff. And lastly, the Lisp interpreter, all right, go check it out if you can. Okay, cool. Any questions? Who heard you? Before mid-sec, yeah. Just much assessment has happened. Okay. Hello.
So, without the limitations imposed by the C standard or the infinite memory, is the secret process of Turing complete?
It would be. Yeah. That's the only limitation, because you can clearly see that before we have the repeat thing. You can scan the tape. It's just that the only thing preventing it from scanning the tape is the preprocessor saying, no, you're not allowed to do this anymore because I've met my limit. Yeah. Hello.
What were the minimum limitations it was placing? You say it had like a minimum recursion depth as opposed to a maximum recursion?
At least. So this one is similar to the one for the BF interpreter, that it does the whole inclusion thing. There are Turing machines that do work on the include method, and then another one that just works in macros. But at least this, like, these are minimum limits, right? There's not really a maximum limit. It just guarantees, like, with any standard, that any conforming implementation must be able to handle this number of recursions. Okay. Anything else? If not, I'll conclude.
Is the finished with 7? Yes.
Sorry.
The programming will finish with 7.
Yeah. Yeah. If I were to run the hello.bf thing, it would probably break my computer because I don't have that much memory. Yeah. But it's good to show that it's actually works. If nothing else, then I'll conclude. Thank you very much.
Thank you for talking, Adriel.
Thank you very much.
You get a mug.
Oh, thank
Do you
you.
have one of these ready?
I don't know.
There you go.
Thank you. Thank you for the
Thanks for coming, everyone. Andrew and the crew have just showed up with Subway, so we're going to carry that up to the Redo. Yeah, that's pretty much it. Come to whatever the thing on Thursday is called, AGM. Yeah, we'll see you guys there, or hopefully at the Redo in a few minutes. Yeah, thanks for coming, everyone. Thanks again, Adriel, for the talk.